Greetings and welcome. Today we're talking about complex numbers. We're talking about imaginary numbers, right? And these are awesome stuff. Awesome sauce. So let's see, complex numbers. We've talked about them a little bit, and we discovered that I is defined as being the square root of -1, right? Complex numbers or imaginary numbers. We'll be able to make the distinguish between those two later today. If you hear any talking, that's probably just my son Everett hanging out with us during this lesson. Yeah, he's having a blast though. So let's see. So this I is equal to the square root of -1. That was our definition of it, and we've been able to do some simplifying with it and things like that. One of the trickier types of problems where I could potentially see an error that I want to just point out. Let's say I've got the square root of -10 multiplied by the square root of, let's say, let's do -15. How about? There we go. Now, according to my previous rules, I guess, I've said that if I'm multiplying two radicals with the same index, you can just multiply their insides, and that actually won't work in this case. So this is not true, so let me do it the wrong way first, if that makes any sense. Because if I multiplied these two insides, -10 times -15 would be 150, all right, positive 150, and then I'd break that up into the square root of 25 times, what's that, 6? So 5 roots of 6. That would be the wrong answer. Let's see, it turns out that I can't multiply their insides because of the negatives just yet. I'm going to have to deal with those i's first. So I have to pluck the i's out, as I like to say. So square root of -1 times the square root of 10 times the square root of -1 times the square root of positive 15. So square root of -1 is I, square root of this -1 is I times I is I squared, and then multiplied by the square root of 10 times 15 is 150. So what I'm able to do, I squared, I will verify for you that I squared, well, let's see, if I is equal to the square root of -1, and I square both sides here, it turns out that I squared is equal to, well, the square and the square root cancel out, and I get -1. So I squared, the funny thing about it is if you square an imaginary number, you get a real number, which is somewhat unusual, right? In a lot of cases, Everett's excited about this. I know, Everett. But I squared equals -1. If you square an imaginary number, you get a real number. In a lot of cases, a lot of sets of numbers, they're closed systems that when you do operations on them, you expect to get another number within that number set, right? So if I add a real number to a real number, I expect to get a real number, right? If I add an integer to an integer, I expect to get an integer, right? But it turns out that for a lot of these imaginary numbers, there are cases in which you could end up with non-imaginary results after doing some operations to it. So let's keep working here. So I squared is equal to -1, and square root of 50 is going to simplify just like I did over here. And so I'm going to end up with -5 square roots of 6. So you can see that this answer was just off by a sign, is what ended up happening. So you do have to be careful. You have to pluck those i's out first. Now let's consider what's going on with these I squared situations here. So let's consider the following. Consider the following. Consider. So, I just said that I is defined as the square root of -1, and I squared is equal to -1, right? So let's actually do some work and figure out what would I cubed equal. All right, so I cubed, I'm going to do some scratch work on the side. So I cubed, I could define as I squared times I, right? Because 2 plus 1 is 3 if I add those exponents. I squared is equal to -1. I is the same as I, so this is going to equal -I. Aha. So I, -1, -I. All right, so hopefully that's enough justification there for us. I to the fourth, let's see what that would be. I think I might have a couple ways, multiple ways I could set this up. I to the fourth, let's say I define that as I squared times I squared. So that would be, well, substitute -1 times -1, which is +1. Interesting. Interessante. So that is +1. Let's say I tried it another way. I could have had, well, what if I wanted to do I times I cubed, right? Because that also would equal I to the fourth. I is the same as I cubed is the same as -I, according to this, right? Bam. And that would equal -I squared. But what's I squared equal to? Well, -1. So this is going to equal, I think I'm running off the screen there, aren't I? Negative of -1, which is +1. So it does seem to verify out in both cases. Now, behold what happens when I try I to the fifth. So I to the fifth is the same as, let's see, I'll give myself some space. So I to the fifth is the same as I to the fourth times I, which is 1 times I, or I. Huh. Peculiar. Peculiar. I to the sixth. I know you're probably wondering, man, we're still going with this stuff? But yeah, this is good stuff. I to the sixth. Let's see, I can think about this a couple of different ways. How about I do it as I squared cubed? And really, any arrangement I found to get 6, I could have done I to the fourth times I squared, but I just felt like doing a power to a power property, right? Because 2 times 3 is 6. So that's I to the sixth is equal to that. What is I squared? Well, that's -1. And what is -1 cubed? Well, 3 negatives being multiplied is still negative. That's -1. Huh. Is what Everett was saying. Everett, can you sing for us? Can you sing? Oh. No? No singing? Well, that's alright, nonetheless. Oh, he's got the cell phone, though. He's pretending to call people. That's okay. Oh, he's pretending to talk, too. So let's see. I to the seventh. Well, here's a quick way I could set that up. That's the same as I times I to the sixth, right? Is I to the seventh. I to the sixth I just found out was -1 and times I, so that's -I. I don't know if you guys are noticing anything unusual yet. Let's do I to the eighth. One last problem. So I to the fourth times, well, I could do I to the fourth times I to the fourth, or I could do I to the fourth squared. I to the fourth we know is equal to 1. So that's 1 squared, which is 1. 1. Now, looking at these, look at what I got. I got I, -1, -I, 1. I, -1, -I, 1. I don't know what you guys' guesses are, but it turns out I to the ninth is going to repeat this pattern. It turns out that this is a 4-term pattern going on here, right? Notice there's a pattern. It's repeating this cycle of I, -1, -I, 1. So I would expect that I to the ninth would be the next one in the pattern. It's going to go back to the beginning and should equal I. Let's see if that works. So let's do I cubed, maybe? What is I cubed equal to? I believe that's -I. Okay. And cube that would be, well, it'd still be negative. It'd be -I cubed. And what's I cubed? Well, that's negative of -I, right? Because I cubed is -I. And negative -I is +I. Is that what I expected that to be? It is, right? I was expecting it to repeat I, like this one and this one, right? So every fourth term is the same, is what we realize. Now, let's do an example problem using this skill. What if I want to figure out what is I to the 21st power? Okay. Now, I could try to figure out this pattern over and over and over again until I go all the way out there, but that's not the most efficient way to do it. But what I want to point out is that I to the 4th is our best friend, right? Because 1 is the coolest number, no matter how lonely it is. So I to the 21st, I'm going to try to break that up into as many I to the 4ths as I can, right? So I to the 4th, let's see, 21 divides by 4 5 times evenly, right? I to the 4th to the 5th, right, would be I to the 20th. And then I need one more I going on there, right? So this would be kind of like my remainder, right? So 4 times 5 is 20, plus 1 is 21. Now what is I to the 4th equal to? Well, that's 1 to the 5th times I to the 1st. And 1 to the 5th is 1 times I equals I. Right, so you're actually able to simplify this without too much difficulty. Let's try one more crazy one like that. Let's do an I to the, let's do 43rd. Oh. So my goal is, because I to the 4th is my best friend, I think that makes it sound like I've got imaginary friends, but I to the 4th is equal to 1, so my friends are real. My friend's a real friend. So I to the 4th is, how many times does that go into 43? I think it goes in 10 times, 10, with a remainder of 3, right? So 4 times 10 is 40, plus 3, 43. So hopefully you're seeing this little setup that I'm doing here. Very strategic in my setup. So I to the 4th is equal to 1. 1 to the 10th times I to the 3rd. What is I to the 3rd? Well, that's equal to negative I. And 1 to the 10th, let's see, I'll do it over here, is 1. 1 times negative I is negative I. So I can actually instantly kind of find out where in the pattern that lands, right? So that's not too bad. Not too bad at all. So, so that's one type of problem that we'll be doing tonight. What about introducing I's in solving? Solve. So let's say I wanted to solve this particular equation. 4x squared plus 36 equals 0. And for this problem, it is a quadratic, so you could try to set it equal to 0 and factor to solve. And I could actually factor this a little bit. Let's actually, well, maybe you would even realize that you could divide everybody by 4. And I'd have x squared plus 9 equals 0. And then you'd try to factor x squared plus 9, and you might remember that there's no such thing as the sum of two squares pattern. No such thing. DNE does not exist. But because I don't have a linear term, I just have a quadratic term, I can actually isolate this term by itself and solve kind of normal fashion. So I'd have x squared equals negative 9. And then to get x by itself, I'd root both sides, plus or minus, don't forget it. And I'll get x equals plus or minus, well, square root of negative 9, I could break that up into the square root of 9 times the square root of negative 1, or square root of negative 1 times 9. And I'll get x equals plus or minus, square root of 9 is 3, square root of negative 1 is I. So it turns out, even solving quadratics now, I'm able to have imaginary results. And here, check this out. Let's do a formal check of this, even crazier. 4 times, let's try the negative version. I'll just plug in the negative. Negative 3i squared plus 36, is that equal to 0? That'd be 4 times, negative 3 squared is positive 9, I squared is I squared, plus 36 equals 0. 4 times 9 is 36, I squared is equal to negative 1. Oh, no, you didn't. What? Let's check this out. This is crazy. No way. No way. 0 equals 0. Cha-ching. It checks out. How awesome is that? Everett's talking in the background. He's excited about I's checking out. So, let's talk about something else. So we've been dealing with kind of purely imaginary numbers so far. Numbers that are have just an I. Let's talk about complex numbers for a minute. Complex numbers. Okay? So complex numbers are actually going to kind of be a type of hybrid. All right? They are any number that can be written in the form, A plus BI. All right? Where A and B are real numbers. So what I want to point out about this is that this A portion is going to be our real part. And the plus BI portion is going to be our imaginary part. Okay, so we end up having this hybrid type of number that is part real, part imaginary. Okay, and still try not to get hung up on the word imaginary. I think I said in another video that it literally was called imaginary out of a mocking sense, where a mathematician was making fun of the fact that some mathematicians believed in these numbers, and he at that time did not see the value in them. He thought it was just kind of like a little game they were playing, but they're very legitimate numbers. I have to be careful not calling them real numbers because I have a definition for the word real, mathematically speaking. So what I want to point out is the complex numbers. Let's actually write down what some would be. So I could have a complex number 2 plus 0i is the same as 2. All right, so there's a real number written as a complex number, right? 2 plus 0i. There were 0 i's attached. I could also have 0 minus 7i, right? Which that's the same as just negative 7i, right? So here's a purely imaginary number that I could also write in the form a plus bi, right? I could also have a complete hybrid number where I kind of have 2 minus 5i, all right? So there is a truly complex number. It's got a real part. It's got an imaginary part. Let me talk about just a little bit of the complex number system. All right, so of complex numbers, maybe I can do this as a Venn diagram. No, I don't think I will. So let's imagine complex numbers. All right, they're of the form a plus bi, right? And within the complex numbers, I've got two types. All right, let's see. I want to make sure I'm not going off the screen here. Oh, I'm golden. Here we go. So I've got two types. I've got real numbers. All right, if b is equal to 0, right, then there was no I part, and I'm just left with real numbers. All right, and of the real numbers, there's, well, I mean, I can break this down in even more subsets if I wanted. But of real numbers, we have rational numbers, which can be written as fractions, right? And we have irrational numbers, which are like the square root of 2, right? An infinitely long non-repeating decimal, right? Like pi or e or square root of 7, stuff like that. Now, then there are imaginary numbers, is the other set. Imaginary numbers, and in those, b is not equal to 0. So imaginary numbers are any number that has an I within it, okay? Imaginary numbers. And within the realm of imaginary numbers, there's two sets as well. There are ones in which if a is equal to 0, those would be, Everett's upset. Everett, don't worry, just because they're imaginary doesn't mean they don't exist. It's okay. It's okay. there are pure imaginary, okay, in which a is equal to 0. So if this part was equal to 0, here's a pure imaginary number, which is a lot of the ones we were looking at earlier, right? So pure imaginary would be like that, right? And the other situation is when a is not equal to 0, all right, which are non-pure imaginary. Okay, like this. All right, but technically all of these are types of complex numbers regardless of a or b equaling 0. Actually, speaking of which, where would the number 0 fit in this category? Right? So 0 would be the same as 0 plus 0i, right? So the 0 part breaks it down over here. 0 is a rational number because I could write it as 0 over 1 or 0 over 10 or 0 over 73, right? That's all 0. So that's where 0 would fit. Figured I'd point that out. Okay, so those are complex numbers. So let's just do a little bit of work with complex numbers, adding, subtracting, multiplying of them. We won't do any dividing today. So, example. Let's say I want to add the following numbers. So 8 minus 5i. So there's a complex number, all right, a non-pure imaginary, and 2 plus I. Now it turns out when I'm adding these, I can just add their corresponding parts. So let's add their real parts. So 8 plus 2, all right. There we are, is 10. And let's add their corresponding imaginary parts. Negative 5i and 1i. How many i's is that? That would be minus 4 i's. So I added 2 non-pure imaginary numbers, and I got another non-pure imaginary number. Not always the case, but it can happen. It can happen. Let's say I've got this. What if I've got negative 3i minus, let's see, the following. What if I've got 2 plus 6i? All right, so here's a pure imaginary, non-pure imaginary. I'm subtracting them. I don't have a real part here, so this is just going to be, well, I could actually even break this apart, distribute this minus sign. So that's negative 2 and minus 6i. So this is going to be negative 2. All right, and negative 3i and negative 6i, those guys are buddies. So I combine them just like I would like terms, right? So that's minus 9i. And so here I had a pure imaginary with a non-pure imaginary giving me a non-pure imaginary. It's not necessarily always going to be the case. Technically, it also could have given me a real number. If this was like a 3i here, or sorry, a minus 3i, they would have canceled out. And that could have happened as well. So let's talk about multiplying real quick. And maybe 2 examples on this. Here we go. What if I've got 4 plus 2i times 3 minus 5i? Now, if I ask you to do this problem, even just by instinct, you'd probably get like 90% of this right. It turns out to multiply these 2 complex numbers, all right, you would FOIL it, or double distribute. So 4 times 3 is 12. 4 times negative 5i is negative 20i. And now let's multiply these. 2i times 3 is plus 6i, and 2i times negative 5i is negative 10i squared, right? So let's simplify these. Well, I've got some like terms here, right? So let's see, I've got 12, negative 20i's plus 6i's is negative 14i, and minus 10i squared. What is I squared equal to again? Guys? Negative 1. What is what Everett's saying? What? What is right? I squared equals negative 1. What? It's ridiculous, is what he's thinking. So negative 10 times I squared, right, it's negative 1. That's positive 10. Woohoo! Is right, Everett. So I can combine that, because that's a real number, I can combine that over here. So 12 plus 10 is going to be 22 minus 14i. And there's my answer. Not bad. Let's see, get some equal signs in here. Let me show you one more case, which is kind of interesting, maybe. Maybe, I don't know. What if I have 5 minus 2i times 5 plus 2i? Last example. So let's multiply this out. 5 times 5. Oh, wait. Oh, maybe you noticed something else already, but that's fine. I'm just going to keep moving on ahead. Plus 10i, right? Minus 10i, and minus 4i squared. So I can combine like terms, and then you might realize, aha, ching, ching, Fruit Ninja those, and I got 25, right, equals, negative 4i squared, that's the same as negative 4 times I squared is negative 1, so that's 25 plus 4, or 29. Look at that, I multiplied two non-pure imaginary numbers, and I got a real number out of it. How absurd. The thing that you might have realized is I conveniently set this up, that was a pattern. I was multiplying two conjugates, a plus b and a minus b, which we all know is equal to a squared minus b squared. So I also could have just done, well, let's do that. Let's parallel dimension this problem here. So I would have said a was equal to 5, b was equal to 2i, and I would just plug it in this pattern. So that would be 5 squared minus 2i squared. 5 squared is 25 minus 4i squared. So that's 25 plus 4, because I squared is negative 1. Maybe I'll write that out. Maybe I'll write that as minus 4 times negative 1. And that's 29. So same difference, whichever you'd get. So if you notice the pattern, that's cool. That might come into play in tomorrow's video. Alright, well, thanks for watching, friends. Hope you had a great day, and use your imagination. Bye-bye.